let's go through one last set of slides to try and understand how gradient boosting works. We have discussed this a few weeks ago. How does gradient descent work? We initialize beta while we wait for some condition to be fulfilled, such as the gradient is close to 0. We find out the gradient, and we take then a step size. How does gradient descent work? We have our loss function. We're trying to get down the hill. We find out which direction we have to move beta to get steeply up the hill, and then unsurprisingly we move beta in the opposite direction. Here we have the gradient of the loss function with respect to beta, and here we take where we were with beta and we move in the opposite direction. So what do? We start with all of our coefficients equal to 0, and then let's see what happens in iteration 1. We move beta 1 by a small bit, beta 2 by a small bit, so that in total, across the whole of the first iteration, we move our estimate for y by the sum of all these small bits of betas times the individual features. So that's our little mini model for the first iteration. When we do the second iteration, we will create another mini model, y2, which will be made up of all the little movements of beta. So let's think where we are after 2 iterations. We have our first mini model, which gave us our estimate for y, but it was only a partial estimate for y. We have our second mini model, which gives us something which we add onto our first estimate for y. And we're going to carry on doing this until we don't get any extra models, because we've reached the minimum. Each iteration that we do adds an extra little bit, as we just said. Here's one, here's another. What can we say about these little bits that we're adding? They are very simple functions. Each one of these itself is a linear model. It's a linear model which is chosen to reduce the errors and so reduce the loss function, but it's still a linear model. And if you look at the sum total of our gradient descent, you have one little linear model, another little linear model. Each step of gradient descent is giving us a Tichy linear model, and when we add them all up, if you add them all up downwards, you will see that the sum of all the movements of the first coefficient gives us the final value for the first coefficient, and so on. So we end up with a big linear model. And that's how gradient descent works. The question we have to ask ourselves is, if it's a good idea to move in the direction of the gradient, why do we only use simple linear models to move in the direction of the gradient? Couldn't we use a more complicated model, and wouldn't that be a good idea? Of course, the final model would be something insanely complicated, because instead of being the sum of linear models, which is just another linear model, it will be the sum of complicated models, adding up to the sum of an insanely complicated model, but it could be a very good predictor. So, here's an idea. Let's start with our model, where we just say our predictions are equal to 0, and therefore our residuals are equal to y. Do the following lots of time. Fit a tree to the residuals. If you fit a tree to the residuals and then you use that tree to predict, and you move in the direction of the predictions that that tree recommends, you are going to move in the direction of the residuals and add that to your prediction, and therefore minimize your residuals. So let's fit a tree to the residuals, but let's not move in the direction of a full tree. This is the equivalent of taking a small step in gradient descent, and in gradient boosting it's called the learning rate, which might be something like 0.01 or even 0.001. It's quite small. The parameter is often called eta. Anyway, once we've built that tree, add the predictions from this tree to all the previous predictions, find the new residuals, and do it again and again and again. So instead of having, as we did with gradient descent, our final model equal to a first little linear model plus another linear model plus another linear model, what we will have with gradient boosting is our final model, equals eta times the first tree plus eta times the second tree, and so on, plus eta times the third tree. Just as an aside, that is not the same as eta times the sum of those trees, because the second tree which is built depends on the first tree which is built, and the first tree was shrunk by eta. There are many implementations of gradient boosting. There's GBM in R, xgboost, which has APIs to it from many platforms, lightgbm, and catboost. We're going to briefly look at three implementations. xgboost, as it's called, from H2O. I think it's written from fresh and H2O actually. lightgbm and catboost. I'm only going to flick through these spreadsheets. I'm expecting you, though, to choose, say, one of these implementations, research it in detail, find out what all the parameters are, and make an effort to understand, look up online, see how people best tune it, and give it a go yourself in our final assignment. I think it would be a bit of a big ask for me to expect you to research all of these three. The one which I had quite a bit of luck with was catboost, but lightgbm has been quite popular, and xgboost itself is a staple diet of many data scientists. I think it's quite nice that xgboost is available to you from within H2O, so if you are sticking to xgboost, you don't have to leave the world of H2O to do your work. Who wrote xgboost, who popularized it in the first place? Yankee Chen. I'm not sure how you pronounce his name. I think the guy is a super guru. He's completely amazing. It was a one-man band that wrote some amazing code, so I've been told. I have to admit I've not looked at the code underlying xgboost. He's got a great tutorial out there, which is written in terms simple enough for me to understand. I mean that honestly. It's got nice pictures, and it doesn't have a lot of maths in it. So I strongly recommend you read his explanation of how xgboost works and all the tricks he put into it to make it as fast as it is today. We'll look at notebook 12a in a little while. lightgbm. The claims of lightgbm: faster training speed and higher efficiency than xgboost, lower memory usage and better accuracy. There's a link here which I'll try to extract and give you on Moodle for your research if you're using lightgbm. We'll flick through them quickly in notebook 12b. Finally, catboost. Catboost is a very glossy product by a company called Yandex. It's got a load of claims which might actually be true. Great quality without parameter tuning, which would be astonishing because it's hard to train the gradient boosting machines. Improved accuracy. It says subject to installation and compatibility issues. I think that must be from the first year when I did this, where we weren't on a Docker image and everyone found it just impossible to install it. I've just been through with the Docker, xgboost, lightgbm, and catboost, and at least for me they all worked. That is it as far as this gigantic slide pack is concerned. I will try to extract the links and put them in Moodle so you can look at the links relevant to the boosting method that you choose, and when I'm going to have a quick flick through some notebooks. But I say again, this is just a quick flick through. I cannot possibly pre-record or go through everything that you need to know to use even one of these. It would just take weeks and it would be boring for you to listen to. What you need to do is go to online help and documents, choose one of them and just give it a go.